Hey, welcome to the Mentored Engineer. In this video, we're going to discuss how to make buttery smooth tracks for your roller coaster. All right, I love roller coasters. You probably already know this if you're watching the channel at all. I think they're great feats of engineering, and I want to talk about how to make buttery smooth transitions because let's face it, some rides out there are awful. Now, when it comes to mind of bad transitions, we're thinking Aero. And Aero gets a bad rap. However, Aero made many fantastic roller coasters for the time. When you go back and you think about the manufacturing processes that existed when they were making their roller coasters, pretty cutting edge for the time. Now we've taken it and with CNC help, we've really gone way beyond. So Aero gets a bad rap, but nonetheless, they still have terrible transitions. Hey, if you like what you see so far, please be sure to smash that like button and subscribe and click that notification bell so I can annoy you at least once a week. Now, the roller coaster I want to talk about was the original Hyper Coaster, which is over 200 feet, and it is still in operation today, and it's still a really good ride. This ride was groundbreaking in so many different ways that it's still talked about today, even though the ride is over 30 years old. This is the one, the only, the Magnum XL 200 at Cedar Point. This is a great ride. However, it has poor transitions. Now, when we talk about transitions, before we talk about Magnum, I want to talk about, let's just drive in our car and we're going to do this one line motion and not have to worry about curving up and curving down. Once we get the one line in there, I think a lot of the other stuff will come out naturally and you can get my concepts as I move from one concept to another. Now, before I go any further, disclaimer here, we're going to do math and we're going to talk calculus. So if those words scare you, please, I'm going to simplify these a whole bunch. So let's talk a little bit about calculus when it comes to moving objects. There are three derivatives of position that we need to look at. First is velocity, then acceleration, and then jerk. So the first one is velocity. So if we take your car's odometer and plotted it out against time, we would see a bunch of peaks and valleys. And as time went on, there'd be a lot of time when the car is just not in use, so it'd be position doesn't change, so it'd be a line. Now, if we looked at the slope of each point on that line, that would tell us the velocity we were going at that time. If we put all those velocity points together and plotted them against time, and we looked at the slope of that line, it'd be acceleration. If we did the same thing, plotted all the acceleration points versus time, and took the slope of that, that would be jerk. So jerk is the what we call fourth derivative of time with respect to position. That's a bunch of math hoo-ha, and we don't really need to know that. However, we are concerned because when we are riding a roller coaster, what we feel is the acceleration. The acceleration is what gets us excited about riding a roller coaster. We want to be pressed down on our seats. We want to be forced up against the harness restraint. We want to get thrown side to side, and all those, what we feel, are accelerations. Those are good things. Now, the derivative of that is jerk, and that is what we don't want to have happen suddenly. Now, what we want to do is spread out the jerks over a greater amount of time, or in our case, track length, so that we don't get sudden, what we call head banging, where you go side to side or front to back, So let's look at an example where we automatically limit the amount of jerk that we see. If we're driving a car and we're sitting at a stoplight and all of a sudden the light turns green, we press the gas and we start going at, let's just say, a constant acceleration. We're being pushed back in our seat at the same rate from 0 miles an hour, let's say, to 40 miles an hour. And then we let off the accelerator and continue on at 40 miles an hour. Now our acceleration is 0 at this point once we get up to the 40 miles an hour. At the 2 points where we first take off and where we stop accelerating, there's going to be jerk there, provided we perfectly put our foot on to the exact right acceleration and then took it off at the exact right moment. When we plot that acceleration versus time, we're going to find out that there's discontinuities in our acceleration, meaning that to get from one point to another, we're going to have a large change in acceleration very quickly, almost instantaneously. And we can do this. So what we're going to want to do is look at the jerk in this, which is the slope of the line at any point. So the slope of all of these line segments are 0. However, in between each one, there is a very, very steep slope, almost infinite, that is going to go off of our chart and then come immediately back down. And you can see those points here. And that's going to happen both when we start and when we stop, and you'll notice that they're in the opposite direction. That's jerk, and that's what we're trying to avoid. Now, inherently, you know that if you were to step on your accelerator at that rate that you wanted all at once, it's not going to be a pleasant experience on your body. So we're not going to do that. You're actually going to ease in gradually to get up to the acceleration you want, stay there constant, and then start easing off when you get to 35, 36 miles an hour, and then just run gently into 40 miles an hour. So that's going to keep the head bombing in your car down when you do this. And we all naturally do it because we like the nice, smooth curves. And what you're doing then is you're taking your jerk plot here and you're kind of smoothing out those big spikes and making them little semicircles or parabolas, if you will. Now let's talk about how Magnum XL 200 factors in here. On the back half of the ride, you enter in this basically hill and valley section where you just continuously go up and down. You get some good pushback in your seat, and then you get some good ejector air time. However, in this transition, well, there's no transition. So what happens is over the length of the ride, you're going to have, if we start at a straight line, we're going to have roughly 1 G. Now, if you're going up, it's going to be less than 1 G, and if you're coming down, it's going to be a little bit more than 1 G. But since the track is straight, you're not really adding any G forces. So it's modeled here as a straight line. Now, what happens when we get to the curved parts of the track, the hills and valleys, is the same as when you tie a rock to the end of a string and then start twirling it around. You have centripetal force. The equation for this is the centripetal acceleration is equal to the velocity squared divided by the radius. On a straight piece of track, your radius is pretty much infinite, and you will have no centripetal acceleration. But in our curves, we have a radius. So in the curved parts, aerodynamics probably wanted a specific G-force. So what they did was they said, what's our G-force? And we'll plan our radius accordingly to get to that. And what happens is you went from a straight piece of track to a curved piece of track in a very short amount of time, almost nothing. And you're going to have a sudden change in acceleration, just like when you accelerated your car. So if we plotted that against the length of the track, we would find out in a straight section you have roughly 1 G. And then we go into a hill where you'd have negative 1 Gs, back to a straight section, 1 G, and then into the valley where you'd have 2.5, 3.5 Gs, and then you go back to a straight section and the process repeats a few times. Well, each one of these discontinuities poses a problem for transition. It's a sudden jerk, and this ride is very jerky in that way. Still very good ride, but it is 30 years old, and our technology, our math skills, our available computing power has drastically changed in that time. So the question now is, how do we prevent jerk from being a problem? So let's look at our car as it's going down the road. So if we're sitting at the light, we have 0 feet per second or miles per hour velocity, and we want to maintain that for at least a little bit as we start accelerating. Then we want to curve up into a nice section, and we want the point at the end to be not only parallel with our straight line velocity, our straight acceleration, but we also want it to be at the same angle. We don't want it to be like this, or we don't want it to be like that. We want it to be at the same angle. So the way we solve this is by making each point in our jerk plot equal to 0 for the specified track length. So this means that jerk would equal to 0 at the length of 0 and the final length of what we want. And you get a curve like this. So what we need to do is we're going to fit a parabola to this equation. So this would be the old formula, ax squared plus bx plus c, and that's what we're going to put in there. Now, what we're going to do is we're actually going to factor this out because it's easier to find the intercepts when you factor it out. So what we're left with is this equation here, c1 times s minus s naught, and that is our function for jerk. Now we can check this by putting in our 2 points, 0 and s naught for s, and making sure that those are both equal to 0. And you can see here that putting one of those will cancel either term out. So now what we're going to want to do is take this equation and expand it a little bit to the equation you see here. Now here's the real calculus-y part, but it's kind of simple. What we now want to find is the acceleration from our jerk chart. And basically the acceleration is the area under the curve, and we use a calculus method to do that. With this case, we are using polynomials. So the way we do that is very simple. All we do is we add one more to the exponent, and then we divide it by what that new exponent is. So our equation here becomes c1 times s cubed divided by 3 minus c1 s naught times s squared divided by 2. Now, the other thing we don't know is how high this is above the x-axis. So we need to add a constant in here to deal with what we call an indefinite integral. This will come in handy in a second. So this is our main equation right here. And it leaves us with 2 questions. What is c1 and c2? So C1 and C2 are very cool variables that allow us to make this more universal. All right, so we've got C1 and C2 in this equation. What do we do with them? How do we figure out what they are? Well, we basically need 2 more equations to make this work, and we call those boundary conditions. So in our case, we want the acceleration to match the previous acceleration in our track segment. So for a Magnum XL, and we're coming from a straight part to a hill, we're going to want that first boundary condition at distance 0 to be equal to 1. So we'd say that. However, in our case, we're actually going to say it's equal to the previous acceleration, which we're going to call a naught. So that's our first boundary condition. Our second one would be, what is the final acceleration that we want? So our acceleration at distance s naught is going to be equal to our final acceleration, which we're just going to call AF right here. So when you solve these equations together, you're going to find out that C2 equals A naught and C1 equals this equation right here. When you combine all that, you get this equation, and this allows you to transfer between any 2 accelerations in a smooth line. In fact, when we plot it out, it's going to look like this. You're going to have very smooth accelerations the entire length of your transition. Now, the really cool thing about this is it doesn't matter what accelerations you're going to use. You can go, as long as you know the beginning acceleration and the end acceleration and how long it is, you can come up with every transition you can possibly imagine. So if you're on a straight section of track going at a certain speed, you can now figure out how to transition between 1G, which is you just sitting there, you don't have any vertical motion up and down, and if you're traveling at the same speed, you have no acceleration. You can now determine how to get to 3Gs, what kind of rotation does that need to be, and it'll be a smooth transition between the 2. So now that we have this, we can start making a plan of different track sections and what Gs we're going to start off with and what we're going to finish and how long that section is. Now the final G is going to be the initial G for the next segment. So we can actually pile these together as you see here in this Excel spreadsheet. And now we can start making a track plan of going up and down hills. We could even do loops with this. The only limitation with this is it has to be in 2-dimensional space. So your roller coaster can only roll straight forward and backwards. It doesn't have any turns. So we're going to stop here, but in our next episode, we're actually going to talk about how we get to our XY coordinates for the entire roller coaster, and more importantly, how we would actually form our rails to make this work. So please join us then. Hey, and if you like this video, please like, share, and subscribe.